And then this vector equation was motivated on the very first day of class by the topic of solving a linear system of equations in the variables x1, x2, up to xn, where then the coefficients of those linear equations would be the coefficients of the vectors. So a11, the second entry in a1, the nth entry in a1, and on the right-hand side here would be the first entry in b, and now all of our quantities would just be scalars. Plus, plus, dot, dot, plus, equals. And then the same thing just with the nth component on the right-hand side and the nth components of all of the vectors on the left-hand side. So actually I have this slightly backwards. Just fix my subscripts. This is the first entry in A2 and the first entry in AN in our first equation. Then we have the nth entry of A1, the nth entry of A2, the nth entry of AN in our final equation. Although those n's need not be the same, because we have seen already some techniques for solving rectangular, not square, but rectangular systems of equations that either have more equations than they have variables, or they might have more variables than they have equations. So rather than n here, let me put instead m, just so that we can distinguish between the two when that distinction is important. Anyway, so this was the background, right? This is where we spent what we did in Chapter 1, really, is figure out how a linear system of equations becomes a vector equation, and then a vector equation becomes a matrix equation. And then once we have a matrix equation, we have a tool for solving that matrix equation, and that is to use an augmented matrix with A, the matrix on the left, and then our right-hand side vector B on the right. And then just use a series of elementary row operations to try to discover the bound variables and discover the free variables, and then to write our solutions where necessary in parametric vector form. Let's call it PDF. So that's where we were. What we spent our time on yesterday was figuring out how a particular vector equation, specifically the vector equation which has on the right-hand side the zero vector. In yesterday's class, we used this, what we call homogeneous equation. Call it homogeneous just because of that zero on the right-hand side. We used the solution, the nature of the solutions of that vector equation, to define what linear independence means. Namely, we're going to say that the vectors a1, a2, up through an are linearly independent, only if what happens? If and only if what happens? What did we say yesterday?
It's linear independent.
Right, if the a1, a2, up to an are linearly independent. Yes, if the only solution to this vector equation is that all the x's must be 0. In other words, this equation has only a trivial solution when the vectors are linearly independent. So today what we want to do is return to our viewpoint of what a matrix means. We saw this in an applet a couple of classes ago, and then we just want to take a little bit of deeper look into that and think about how a matrix, and then by extension a matrix equation, and by extension a vector equation, represents a transformation from a domain into a codomain. So how do we think of a matrix as representing a function somehow? That's the name of the game today. And when a matrix represents a function, we're going to call that function a linear transformation. And then if we somehow produce a linear transformation from out in the real world somewhere, then how do we translate that linear transformation into a matrix? This sometimes goes by the name, at least I like to call the name of this correspondence that we're going to be investigating today, the fundamental theorem of linear algebra. It's that important in my book. And it's going to be the relationship between these two things that we're talking about today. And it goes like this. even though we haven't defined these terms yet, let me get this on the table. So if T is a linear transformation from an n-dimensional space, let's say, into an m-dimensional codomain. So if this T is a linear transformation, there's the hypothesis of the theorem. Then there exists a matrix. Take the red pill. Don't know if that reference is getting too old already. There exists a matrix A. And this matrix is going to have m rows and n columns. So let me add that up here. M by n. There exists an m by n matrix A such that the action of this linear transformation T on a vector x is exactly the result of multiplying that vector by the matrix A. In other words, the content of this theorem is that any linear transformation that we wish to talk about, it is just as simple to talk about a matrix instead. That every linear transformation can be represented by a matrix, and conversely, every matrix represents a linear transformation. And the difference between the two viewpoints is that we typically tend to think of T, the linear transformation, as being a function. After all, we're using this function-style notation up here to describe its domain and its codomain. But when we think of A as a matrix, that this operation of A on X is just matrix multiplication. So it's something much simpler, because functions can be complex. But multiplication is usually pretty straightforward. Right? So that's the real benefit of the fundamental theorem of linear algebra, is instead of thinking of linear transformations as functions, we can think of them as matrices. And then life gets a lot easier, because we're developing a lot of tools for how to work with matrices. But the fundamental theorem also guarantees us, well, it doesn't guarantee us, but at least it suggests that if I have a question about a linear transformation, I can translate that into a question about its matrix. And answering questions down here is a lot easier than answering them up here. So if I want to know something about a linear transformation, I should probably find a matrix for it and then do something pretty simple, usually, to that matrix. Maybe I should row reduce it, or maybe I should figure out sort of how many free variables does it have, right? These basic questions that now we know how to answer for a matrix are now going to tell us something about the linear transformation that corresponds to that matrix. So that's the name of the game today.